Hello friends, I am Professor Yogesh Chaba from Department of Computer Science and Engineering, Guru Jambeshwar University of Science and Technology, Hisar, Haryana. In this lecture, we will study about email security protocols. First of all, please see the contents which I shall cover. After covering brief introduction about email security, I shall take up different email security protocols like Pretty Good Privacy (PGP), Privacy Enhanced Mail (PEM), and Secure Multipurpose Internet Mail Extension (SMIME). In last, we will compare all these protocols. Electronic mail, most commonly referred to as email since 1993, is a method of exchanging digital messages from one sender to one or more recipients. Email operates across the internet or across other computer networks. Email privacy is the broad topic dealing with issues of unauthorized access and inspection of electronic mail. This unauthorized access can happen while an email is in transit as well as when it is stored on email server or on a user computer. Email has to go through potentially untrusted intermediate servers before reaching its destination, and there is no way to tell if it was accessed by an unauthorized user or not. Email system is different from a letter sealed in an envelope, in which by close inspection of the envelope it might be possible to tell if someone opened it or not. In that sense, an email is much like a postcard whose contents are visible to everyone who handles it. There are certain technical methods that make unauthorized access to email difficult, if not impossible. However, since email messages frequently cross nation boundaries and different countries have different rules and regulations, so email privacy is a complicated issue. This problem has stimulated several people and groups to apply the cryptographic principles to produce secure email. Now, we will study few common widely used email security systems: Pretty Good Privacy (PGP), Privacy Enhanced Mail (PEM), and Secure Multipurpose Internet Mail Extensions (SMIME). First of all, let us see Pretty Good Privacy. PGP, short for Pretty Good Privacy, is a public key encryption program originally written by Phil Zimmermann in 1991. Over the past few years, PGP has got thousands of adherent supporters all over the globe and has become a de facto standard for encryption of email on the internet. Released in 1991, PGP is a complete email security package that provides privacy, authentication, digital signatures, and compression, all in an easy to use form. Furthermore, the complete package, including all the source code, is distributed free of charge via the internet. Due to its quality, zero price, and easily availability on Unix, Linux, Windows, and Mac operating system platforms, it is widely used today. PGP can be used to send messages confidentially. For this purpose, PGP combines symmetric key encryption and public key encryption. The message is encrypted using a symmetric encryption algorithm, which requires a symmetric key. Each symmetric key is used only once and is also called a session key. The message and its session key are sent to the receiver so that they know how to decrypt the message, but to protect it during transmission. It is encrypted with the receiver's public key. Only the private key belonging to the receiver can decrypt the session key. PGP supports message authentication and integrity checking. The latter is used to detect whether a message has been altered since it was completed, and the former to determine whether it was actually sent by the person or entity claimed to be the sender. Because the content is encrypted, any changes in the message will result in failure of the decryption with the appropriate key. The sender uses PGP to create a digital signature for the message with either the RSA or DSA algorithm. To do so, PGP computes a hash, also known as a message digest, from the plain text and then creates the digital signature from that hash using the sender's private key. To see how PGP works, let us consider the example shown in figure. Here, Alice on the left hand side wants to send a signed plain text message P to Bob on right hand side of figure in a secure way. Both Alice and Bob have RSA type of private and public key D and E. Let us assume that each one knows other's public key. Alice starts out by sending message P by invoking the PGP program on her computer by first hashing her message P using MD5 and then encrypts the resulting hash using her private RSA key DA. This signed hash of P is concatenated with original message P resulting P1, which is transmitted after compressing by zip program giving output P1.Z. On the receiver side, Bob receives P1.Z message, which is given to International Data Encryption Algorithm IDEA module for decryption. When Bob eventually gets the message, he can decrypt the hash with Alice public key E and verify that the hash is correct. After decompressing it, Bob separates the plain text from the encrypted hash and decrypts the hash using Alice public key. If the plain text hash agrees with his own MD5 computation, he knows that P is the correct message and it came from Alice. After verification of hash function, Bob reverses the base 64 encoding and decrypts the IDEA key using his private RSA key. It is worth to note that RSA is only used in two places here: to decrypt the 128-bit MD5 hash and to encrypt the 128-bit IDEA key. Although RSA is slow, it has to encrypt only 256 bits, not a large volume of data. Thus, PGP provides security, compression and a digital signature, and does so in a much more efficient way. PGP supports 4 RSA key lengths. It is up to the user to select the one that is most appropriate. The length are: number 1, casual 384 bits, it can be broken easily today. Number 2, commercial 512 bits, it is breakable by 3-letter organization. Number 3, military 1024 bits, it is not breakable by anyone on this earth. Number 4, Allen 2048 bits, it is not breakable by anyone on other planets also. Since RSA is only used for 2 small computations, everyone should use Allen strength keys all the time. The format of a classic PGP message is as shown in figure. Numerous other formats are also in use. The message has 3 parts containing the idea key, the signature and the message respectively. The key part contains the key identifier and key itself. The signature part contains a signature header followed by a timestamp. Next field is the identifier for the sender's public key that can be used to decrypt the signature hash, and this field is followed by type information that identifies the algorithms used and the encrypted MD5 hash itself. The message part also contains a header followed by the default file name to be used if the receiver writes the file to the disk. Next field is message creation timestamp, and finally the message itself. This was about working of PGP algorithm. Now let us see a product that is OpenPGP, which is being used nowadays based on PGP algorithm. OpenPGP is the most widely used email encryption standard in the world today. It is defined by the OpenPGP Working Group of the Internet Engineering Task Force IETF, standard RFC 4880. The OpenPGP Alliance is a growing group of companies and other organizations that are implementers of the OpenPGP proposed standard. The alliance works to facilitate technical interoperability and marketing synergy between OpenPGP implementations. The OpenPGP standard was originally derived from Pretty Good Privacy PGP protocol. RFC 4880 document contains all the necessary information to develop interoperable applications based on the OpenPGP format. It describes the format and methods needed to read, check, generate and write conforming encrypted messages, keys and signatures. In July 1997, PGP Incorporation proposed to the IETF that there should be a standard called OpenPGP. They gave the IETF permission to use the name OpenPGP to describe this new standard as well as any program that supported the standard. The IETF accepted the proposal and started the OpenPGP working group. OpenPGP is on the Internet Standards track and is under active development. Specification of PGP was RFC 1991, but the current specification in OpenPGP is RFC 4880 in 2007, the successor of RFC 2440. The standard was extended to support Camellia cipher by RFC 5581 in 2009 and encryption based on elliptic curve cryptography as RFC 6637 in 2012. OpenPGP's encryption can ensure secure delivery of files and messages as well as provide verification of who created or sent the message using a process called digital signing. Using OpenPGP for communication requires participation by both the sender and the recipient. OpenPGP can also be used to secure sensitive files when they are stored in vulnerable places like mobile devices or in the cloud. So, after PGP, let us move on to Privacy Enhanced Mail PEM. In contrast to PGP, which was initially a one-man show, our second email security protocol, Privacy Enhanced Mail PEM, is an official internet standard and described in 4 RFCs, RFC 1421 through RFC 1424. It is a 1993 IETF proposal for securing email using public key cryptography. Very roughly, PEM covers the same territory as PGP, that is privacy and authentication for RFC 822 based email systems. Nevertheless, it also has some differences from PGP in approach and technology. PEM is the outgrowth of work by the Privacy and Security Research Group PSRG of the Internet Research Task Force IRTF. Messages sent using PEM are first converted to a canonical form so that they all have the same conventions about white space like tabs and spaces. Next, a message hash is computed using MD2 or MD5. Then the concatenation of the hash and the message is encrypted using DES. In light of the known weakness of a 56-bit key, this choice is certainly suspect. The encrypted message can then be encoded with base 64 coding and transmitted to the recipient. As in PGP, each message is encrypted with a one-time key that is enclosed along with the message. The key can be protected either with RSA or with triple DES using EDE. In PEM, key management is more structured as compared to PGP. Keys are certified by X.509 certificates issued by CAs, which are arranged in a rigid hierarchy starting at a single root. The advantage of this scheme is that certificate revocation is possible by having the root issue CRLs periodically. The only problem with PEM is that nobody ever used it and it has gone to that big bit bin in the sky. Although PEM became an IETF proposed standard, still it was never widely deployed or used. The problem was largely political. Who would operate the route and under what conditions? There was no shortage of candidates, but many people were afraid to trust any one company with the security of the whole system. The most serious candidate, RSA Security Incorporation, wanted to charge per certificate issued. However, some organizations balked at this idea. In particular, the US government is allowed to use all US patents for free, and companies outside the US had become accustomed to use the RSA algorithm for free as the company forget to patent it outside the US. No one was ready about suddenly having to pay RSA Security Incorporation for doing something that they had always done for free. In the end, no route could be found and PEM collapsed. In addition to being an obstacle to deployment, the single rooted hierarchy was rejected by some commentators as an unacceptable imposition of central authority. This led Phil Zimmermann to propose the Web of Trust as the PKI infrastructure for the encryption program Pretty Good Privacy (PGP). Efforts to deploy PEM were finally abandoned in response to the need to extend the protocol to support MIME. This led to the development of the protocol MIME Object Security Services (MOS) and SMIME, which shares de facto standard status with PGP. This is an IETF standard, a result of a group working for a long time. The basic idea is to have privacy by virtue of hierarchical authentication. A receiver trusts the message of the sender when it is accompanied by a certificate from his trusted authority. These authoritative certificates are distributed from a group called Internet Policy Registration Authority (IPRA) and Policy Certificate Authority (PCA). These trusted authority actually certifies the public key sent by senders. Now, after PEM, let us see third email security algorithm, that is Secure Multipurpose Internet Mail Extensions (SMIME). IETF next venture into email security, known as Secure Multipurpose Internet Mail Extension (SMIME), is described in RFC 2632 through 2643. As we know, internet email messages consist of two parts, the header and the body. The header forms a collection of field or value pairs structured to provide information essential for the transmission of the message. The structure of these headers can be found in RFC 822. The body is normally unstructured unless the email is in MIME format. MIME defines how the body of an email message is structured. The MIME format permits email to include enhanced text, graphics, audio and more in a standardized manner via MIME compliant mail systems. However, MIME itself does not provide any security services. The purpose of S/MIME is to define such services. Like PEM, it provides authentication, data integrity, secrecy and non-repudiation. It also is quite flexible, supporting a variety of cryptographic algorithms. Not surprisingly, given the name S/MIME integrates with MIME, all kind of messages to be protected. Secure multipurpose internet mail extensions is a protocol that adds digital signatures and encryption to internet MIME messages. A variety of new MIME headers are defined, for example, for holding digital signatures. IETF definitely learned something from the PEM experience. S/MIME does not have a rigid certificate hierarchy beginning at a single root. Instead, users can have multiple trust anchors. As long as certificate can be traced back to some trust anchor the user believes in, it is considered valid. S/MIME uses the standard algorithms and protocols. Now, in last, let us see comparison of email security protocols. We have studied 3 email security protocols. First was PGP, that is Pretty Good Privacy. Second was Privacy Enhanced Mail, PEM, and third was S/MIME. As already discussed, PEM could not gain popularity due to its shortcomings, so it got collapsed. PGP and S/MIME, which was adopted as an internet standard, are 2 official email security systems which are currently National Institute of Standards and Technology NIST specified standards. Both are considered to be secure mail transmission techniques. There has been a great deal of confusion in public and even within the IETF about the status of S/MIME and PGP. Let us compare S/MIME version 3 and OpenPGP protocol, which are widely used nowadays. Please see the figure. Although they offer similar services to the users, the 2 protocols have many differences. S/MIME supports binary format, whereas OpenPGP supports PKCS7 MIME format. Further and more important, to corporate users, they have different formats for their certificates. As you can see, S/MIME supports binary certificate based on X.509 version 3, whereas OpenPGP supports previous PGP based binary certificates. This means that user of one protocol cannot communicate with the user of other, and also they cannot share authentication certificates. S/MIME supports Diffie-Hellman with DSS or RSA, but OpenPGP supports LGAML with DSS signature algorithm. Both the protocol supports SHA-1 hash algorithm. S/MIME supports CMS format of MIME encapsulation of signed data, but OpenPGP supports ASCII. The difference between the 2 protocols is similar to the differences between GIF and JPEG file. They both do basically the same thing for end users, but their formats are very different. So friends, this was about protocols for email security. In this lecture, after covering brief introduction about email security, we discussed different email security protocols like Pretty Good Privacy (PGP), Privacy Enhanced Mail (PEM), and Secure Multipurpose Internet Mail Extension (SMIME). In last, we also compared two most commonly used protocols, SMIME version 3 and OpenPGP. Thank you.